Good afternoon everyone. Today we are discussing specific magnetic loading and specific electrical loading selection or factors affecting the selection of electrical loading and selection of magnetic loading. So in last lecture we have seen the output equation Q is equals to C0 D square L into Ns. So D square L is equals to Q divided by C0 into Ns. Here, how to calculate this D and L? This is here D square and L. Now, for this, we require some specific ratio or some selection factors. So, first is the ratio of L by tau. In last lecture, we have seen the tau and L. L is the length of stator core, and tau is the pole pitch. Now, see here, we know that tau is equal to pi d divided by p. Okay. For this, the induction motor, for example, if the induction motor is designed for low cost or minimum cost, the value of this ratio L by tau for minimum cost L by tau lies between 1.5 to 2. For good power factor, the value of tau in the range of 1 to 1.25. For better efficiency is lies between our standard value is 1.5, and for overall design, for overall design, it is selected as 1. Now see here, the ratio L by tau, suppose selected as 1. So L is equals to tau. Okay, but we know that tau is pi d divided by p. Okay, so this is the selection factor. Depends upon the cost of motor. If the motor is designed for minimum cost, then the value of this ratio is lies in this range. Then if the power factor, it depends upon the power factor, so the value of L by tau lies 1 to 1.25, and for better efficiency and for overall design it is selected as 1. Okay, now next part is your choice of specific magnetic loading, or it is also called as factors affecting selection of magnetic loading. So what are the factors, various factors affecting for selection of magnetic loading? So magnetic loading is nothing but a BAV. Suppose the BAV, value of BAV is higher selected, or first factor, what are the factors affecting? So first factor is power factor. If the value of BAV is increased, the air gap fluxes between stator and rotor is increased. So if the higher value of BAV, so magnetizing current of induction motor will increase. Therefore, the power factor of the motor will decrease. Power factor of motor will decrease. Second is iron loss. If the BAV is increased, the iron losses of the machine will also increase, because because the flux density is directly proportional to eddy current loss and hysteresis loss. So iron losses will also increase. And third factor is overload capacity. If the value of BAV is increased, the overload capacity of the machine is also increased because the air gap fluxes in the stator and rotor is increased. So the overload capacity of motor is increased. So the standard value of BAV lies between 0.3 to 0.6 Weber per meter square. This is the standard value. If the motor is designed for lift, crane or heavy duty cycle, so in that case it is 0.3 to 0.6 Weber per meter square. So next part is choice of specific electrical loading. So in case of choice of specific electrical loading, first factor is your copper losses and temperature. Now suppose if the specific electrical loading is increased, means the specific loading is AC is denoted Iz, AC is equals to Iz into Z divided by pi d. So if Iz and Z is increased, the product of conductor, number of conductor and current flowing through the conductor is increased, therefore the AC value is increased. If AC is increased, the copper losses also increased, and therefore the copper losses is nothing but the power loss due to heat, means temperature also increased. Okay. Then the next factor is voltage. Now the voltage for higher voltage rating machine, we normally know that the various types of induction motor are the rating of voltage rating of 400 volt, 440 volt. But in case of a large industry or power plant, the rating of induction motor or the terminal voltage rating may be lies 11 kV, 6.6 kV, 3.3 kV. So in that case, the value of AC is reducing if the voltage rating is increased. And third, again, the overload capacity. In case of electrical loading, the higher value of AC, the overload, if the higher value of AC is used, means specific electrical loading is increased, then the overload capacity of induction motor is decreased, because Iz into Z again, the current of motor is increased, then overload capacity of machine will decrease. Okay. In next part we will see the problem on mean dimension of induction motor. So this is the first problem on the mean dimension of induction motor. See, they calculate the diameter and the length of stator core for a 3-phase 120 kilowatt 220 or 2200 volt 50 hertz 700 rpm star connected slip ring induction motor with following data. Now efficiency is 92%, power factor is 86%, means 0.86, L by tau ratio is 1.25, and winding factor Kw is 0.955, BAV is equals to 0.48 Weber per meter square, and electrical loading, specific electrical loading is AC is equals to 26,000 ampere conductor per meter. So we start. Let the output is given in kW, power is given. So convert first of all, Q is equals to P divided by eta into cos phi. So P is 120 into efficiency 0.92 into power factor 0.86. So the Q value in kVA is 151.67 kVA. Now, what will be the next step? So, NS, calculate NS. We know that the output equation of induction motor Q is equals to C0 D square L into NS. So, calculate, first of all, we calculate Q, then calculate next C0. So, C0 is equals to 11 BAV into AC into kW into 10 raised to power minus 3. So substitute the value. C0 is equals to 11 into 0.48 into 26,000 into kW 0.955 into 10 raised to power minus 3. So C0 is equals to is a 131.10. The next factor is NS. So we know that a 700 RPM of motor. So what will be the number of poles? So it may be a 8-pole machine. So in this NS is equals to 2F by P. So 2F, substitute 2 into 50 divided by P. P is the number of poles, so 8-pole machine. So the value of F is 12.5 RPS. So after calculating this part, calculate D square L. So D square L is equals to Q divided by C0 into NS. Now substitute the values. Q is your 151.67 divided by 131.10 into 12.5. Okay. Now to calculate the D square L, the value of D square L. D square L is equals to 0.0925. Now we know that in your problem L by tau is equals to 1.25. Therefore L is equals to 1.25 tau. So L is equals to 1.25 into pi into D divided by P. So L is equals to 1.25 into pi into D divided by 8. So L is equals to 0.49 D. Then substitute the value of L in this equation. So 0.49 D cube is equals to 0.0925. So value of D is equals to 0.57 meter. Now this value of D substitute in this equation. So L is equals to, substitute in this equation, then L is equals to 2793 meter. So this is the main dimension of stator, D and L. Okay, so it may be understand with the help of diagram. So this is the inner diameter of stator. So D is equals to 0.57 meter, and the axial length 0.279.